So first off, we started with T.H. Hayden, the guy from Germany. That was his design there on the upper left. And we found that water doesn't really flow very well in January, so those ended up freezing. So we moved to design on the upper right, where it's completely removing those and filling up inner tubes with the cords that come out of the digesters. So eventually we'd like to run something like a bladder or the design they use in India there, where the tank moves up inside the larger tank, and with that method you can just extract as much as you want at any time. So here's a tour through our greenhouse. Should work here.
Greenhouse, and over here we're testing the mixture of effluent on these ones. Every other one has effluent, and the other ones are just pure water. The effluent's coming from tank number 4, and we mix it with a little bit of water. And as you can see, the ones with effluent are growing a lot higher. This is radishes here, and this is carrots. The carrots are growing pretty high too. And this is lettuce.
Now we started doing this because every time you feed the digesters you have to take an equal amount of effluent out, and originally we were just dumping it down the drain, but it's very rich in nitrogen, which gives it really high potential for a fertilizer. So we decided to test that out. Our current ratio is 1 cup of effluent per gallon of water, so 1/16. And so far it's been very effective.
And
we chose lilies as one of our groups because even though they won't necessarily provide anything when they're through, they're very sensitive to nutrient levels in their soil.
And those are also lilies.
Yeah, those are our lily seedlings, so we can track the effects of effluent from a very early stage.
So this greenhouse is located in we call it our energy center. It's like a building that the school built for us to do different science projects outside of it. So the next test we did is yesterday we took a H2O test, and we just used the biogas to heat 10 milliliters of water, and we timed it, and this is what this next video is.
Hi, I'm Greg Baylor with the Cordova High School's methane project. These are my fellow students.
James Allen. I'm Ben Americus.
And we're going to test out some biogas today. We've got our inner tubes full of methane, biogas collected straight from the digesters, a simple hose, and our makeshift Bunsen burner. And over here we've just got 10 milliliters of water and a test tube, a thermometer, and Ben will be timing us. Back to 20 degrees Celsius. And we'll shut the lights off. James, adding pressure out of the tube. Ready to time?
Okay, wait 1 second. Go for it.
1, 2, 3, go.
15 seconds right now.
About 25 degrees. We're getting starting to boil up on top.
About 30 seconds.
Temperature up to climbing to 50 degrees. We've got a nice rolling boil.
At 45 seconds.
And as you can see, we have fittings for this gas all around the classroom. We can hook it up for Bunsen burners at any point, and all this gas has been produced on site using cafeteria cracks. And as you can see, it burns very clean, and there's no sterile bile. So this is a self-contained efficient energy source for experiments such as this.
That's the power of biogas. So our final video here is, as I mentioned earlier, Saturday night we actually got my parents' gasoline lawnmower to run off of biogas straight from our digesters. So I'll show you that here. I'm Ben Americus, and this is my colleague James Allen, and we have an inner tube full of methane that we collected from our biogas digester. And we got this little cord from here, connected on this other cable, and we electrotaped it shut. Then we got another cord right here that comes into the fuel intake, and that's shut closed, so hopefully it'll block all the gas from leaking. And I guess we're going to try to get this to run right now.
Yeah.
So that's it for our presentation. If you have any questions, we'd like to answer them now.
Well, thanks. Have you estimated how much biogas Cordova could make? Has anyone ever kind of looked at that, or is that for ASAP to look at?
That's sort of part of the purpose of this study, is to try to figure out how to do that, how to get an estimate of how much we could produce. One idea was out there that we could use cannery waste from the fisheries for a sort of municipal-sized generator.
Craig, how much would you estimate the cafeteria waste is per day at Cordova High School, for example?
How much waste we get, or how much biogas we produce?
Well, how much food scraps are you collecting from day to day?
About half to 3/4 of a trash can, so 20 to 40 gallons, I'd say.
Is your when you put the scraps into the digester, do you somehow, open a hatch and put some stuff in and then reseal it, or and then it's just a simple mechanical question? That's all.
Yeah, you can see these tubes right here. This is a cap on the feeding tube. We just take it off, pour it down, put it back on. It's nearly airtight.
So you really don't lose any gas when you do that?
No. The feeding tube also goes all the way through this tube to about 6 inches below the bottom. So anything that come out would be water before biogas, so we're not losing any.
That's a good idea.
Yeah, I have two questions. One, can you talk about smell? And two, where do you get the psychrophiles from?
Smell is pretty bad. This would be really hard to contain a household or something like that. You'd want to keep it either outdoors like we did, or downstairs in the basement where you could heat it. And then the psychrophiles, we collected them from Goldstream Lake in Fairbanks. And the mesophiles were from a farm in Delta Junction there. But in our own lake Eek, in our town there, they have a methane pocket, so eventually we'd like to get some of the psychrophiles out of that lake.
If this were to go in a home or a building, actually, there are a few things you could do to reduce the smell that we can't. Obviously, the first is just to keep it clean. We are doing that as much as possible. A big one would be to cart away the effluent as soon as it comes out. We're storing it in 5-gallon buckets at the site for use in the greenhouse. But if we could just take that away as soon as we can and rinse the bucket out and put it back, as well as just having a smaller facility that's much easier to keep clean, I think that would help the smell.
Somebody mentioned that the bacteria that you're using, the cold weather ones, are 4 times more efficient. And what does that mean? Do they produce 4 times as much methane for the food that they're fed?
Yeah.
Works.
I think this is really
really great and exciting. I'm wondering if you have any results yet in terms of, say, different temperatures and performance, you know, when it does better or worse or things like that.
We have established that warmer is better, but I'd like to note that the psychrophiles in the cold room are producing biogas. The mixed tank and the methanogens in the cold room are not, as we sort of expected, because that's below where they should be producing. But we are making biogas at 15 degrees Celsius, although there is more at 25.
Thank you, and congratulations also. This is an amazing project to have so many students involved with. I was really impressed with the fact that you guys were also in Seward just 2 weeks ago at the National Ocean Sciences Bowl presenting. So these guys are really doing a lot of extracurricular work here. I was going to make a comment. I was involved in a lot of these projects, biogas in Yunnan province in China a few years ago, and we found the most efficiency there was when you co-mingled or co-produced gas in conjunction with livestock applications. And I just suggest as you think about scaling up here, it's great to look at the greenhouse applications of nutrient, but also to think about cogeneration with animal livestock production, perhaps a pilot project in somewhere like Palmer or at Delta Junction where you've got livestock sort of kept indoors. There's a really efficient use of that, and you tend to find all sorts of new variables you can add into this, and certainly in terms of getting rid of the smell or the waste part of this, it's a pretty effective system, and there's a lot of documentation I can share with you from Chinese experience.
So how do you guys see this going towards commercial? Like after you guys study, is it like a plan to like try to like be in the commercial phase, or is that not really determined yet?
Well, before we start working on commercial phases at all, we have to see if it's economically feasible, which is kind of the point of the study. But if we were to move it up to a larger scale application, we would probably just be using either municipal cannery waste and maybe even have a communal food scrap dump or something along those lines.
The goal, as stated in this study, was for a smaller scale, individual homes sort of thing. So I think that's where we'd be focusing first. Ben mentioned the handbook on how to build your own. We're still working on the designs, gas collection, and use. From there, you could go, like you said, to the farms in the valley, or you could use fish waste, or really anything organic. And really in whatever scale you wanted to.
So clearly a big part of your study is testing the feasibility, but from what you know now, what is the biggest barrier to use in rural homes in Alaska at this moment? You know, if there are 28 million between India and China being used, is the cold temperature the biggest barrier, or if not, what are the other things that you suspect are keeping them from working right now?
The cold is good, and also just awareness. There's not very many people know about these up here. Yeah, cold and transportation, I think. You do have to get some mud to start your culture from somewhere. Although, after you do that, you can actually use effluent to start more cultures. So you'd only need one initial supply of mud or manure.
More questions?
So are we done here then? Thank you so very much. Really very inspiring. And yeah, I guess what I wanted to say, just one other comment, is like with the Sea Alaska project, where it was a proven technology but not applied here, another one of the goals was really in this idea of sort of spreading the excitement and understanding of these kinds of technologies with young people in particular. This was really, I mean, I remember reading your guys' application when it first came in, and everybody really sitting around that table said, wow, this is really exciting, both from the technology side and from the human side. And while we are talking, of course, about technologies, we really can't ignore the human side of that. So this is really just outstanding work, and I've seen you guys present over to